So we'll now start the session related to using and building AI, and this is the AI-powered advancements section. And our very first speaker is Hui Li with Autodesk. Hui is a senior principal scientist at Autodesk Research, where her research focuses on robotic learning, including topics such as reinforcement learning, imitation learning, that's it, sir, it's a challenge somewhere, foundation models for robotic manipulation. Prior to Autodesk, Hui led the R&D team in Airware, building computer vision and machine learning capabilities for commercial drones, and spearheaded robotics research at Boeing, building agile robotic platforms for airplane manufacturing. She holds a PhD in AI from MIT and has published numerous articles at top AI and robotics conferences and journals. Please join me in welcoming Hui Li.
Thank you very much for the kind introduction. It's my great pleasure to be here giving a talk on deep learning for robotic manipulation. It has been my research topic for several years, and it's also a really exciting topic because there has been so much advancement happening in this area, and exactly powered by the advancement in AI and deep learning. So let's see some examples, right, of the state-of-art robotic manipulation. On the left, you see work from Toyota Research Institute on kitchen tasks using Franca Panda robot arms. In the middle, you see work from DeepMind using the Aloha system, doing some very complex tasks. And on the right, you see work from Stanford University using their custom gripper interface called UMI. So I want to point out two main really incredible capabilities these examples show. One is how general these systems are. So it's the same trained model. They can accomplish like a variety of very different tasks. And then two is how robust these systems are to changes in the environment. Changes, like there are human disturbances, and there's uncertainty inherent in the tasks. So this kind of generalizable and adaptive behavior can only be learned, not programmed. So how does it work? It's learned from human demonstrations. So here you see, this is the Aloha teleoperation system developed at Stanford University and open sourced. Each task approximately requires 200 demonstrations like this. And here you see Tesla. And this is where you see a factory of humans giving human demonstrations in VR headsets. It's a little dystopian looking. So the neural network architecture that's most commonly used for training such imitation learning models is the diffusion transformer, or DIT. It combines the diffusion process and the transformer architecture. And because it's a transformer, it scales really well with model size and data. Many well-known applications uses this architecture. For example, Sora from OpenAI. So we've seen those work we've seen so far is really exciting, very impressive. But let's shift gear a little bit and now look at robotic manipulation from a slightly different angle. So the tasks we've seen so far are mostly household tasks, but what about industrial tasks? For example, assembly tasks that are notoriously difficult. Also, is it possible for us to learn with less human labor 200 human demonstrations per task is non-trivial. And thirdly, can we learn everything in simulation? Because in simulation, things can be sped up, can be parallelized, and then we deploy things in the real world. So for the past few years, my research focus has been trying to answer these questions. Some examples of the industrial tasks here. There's assembly tasks in construction, architecture, also in manufacturing. So, and also if we want to sort of involve less human labor, less human demonstrations, let's look at reinforcement learning. So for those who are not familiar with reinforcement learning, here's a little primer. Reinforcement learning is a machine learning paradigm where the agent takes actions in an environment to maximize rewards. It sort of mimics the trial and error process that we humans learn. And here, for example, our little robot agent needs to go through a maze. And at each time step, it will take an action and observes what happens. It has a new state in this environment. And then it also gets a reward. Sometimes it doesn't get a reward until the end, but there's a harder situation there. But the robot's job is to figure out the sequence of actions to maximize the total reward. And one cool thing about RL is that you can set up the simulation you can set up the environment in simulation and parallelize this trial and error process. And so learning can be immensely accelerated. Here I'll show one of our early works that was published at IROS a few years back. And mainly we have these questions, like in an assembly task where you want the robot to learn how to assemble something, can we just use the sense of touch to learn? So imagine when we put something together, we close our eyes, we can still do it. So here's this idea. Here we propose this approach where we think, well, the learned policy doesn't have to be bound to a specific robot embodiment. It can be, what if we just have the end effector there, we have the force sensor mounted there, and then we can transfer this learned policy on different robot embodiments. So that's the idea. Here's our distributed RL architecture. I won't go into details here due to time limit. But here you see the same trained policy can be deployed on different robot arms and also with different offsets and noises, as well as different target locations. So and then we apply this approach to architectural construction. So this work was a collaboration with the architecture group at ETH Zurich. The vision of this project is to have the robot learn how to build a structure by assembling tight-fitting timber joints together. And so we learn everything in simulation. We collect just a few human demonstrations to guide the RL training. And this is RL training in progress. So, for the first probably 80% of the time, it's doing not so well. I often think like if this were a human, we would be so frustrated and pulling hairs during this process. But then over time, it learns how to put this together, and the reward gets higher, and the success rate gets higher. So in the end, we have a policy that has almost 100% success rate. And then let's deploy the simulation learned policy on the real robot, putting the timber pieces together, right? So we tested the policy on, with small offsets in the position, in orientation, and also tested what about different angles of the joints. We're trained on the 90-degree joint angle. We can run this on a 75 or 60-degree angle, and it can still work. 45 is the max of the difference. So we can also train this with different joint type, maybe like an H-shaped double joint, different joint type for the timber structure that we want to build, and deploy that on the real robot. So that was a work collaboration with ETH. The next one I want to show, this was an intern project from last summer. How do we transfer from sim to real on really difficult insertion tasks? For example, this is like a skateboard truck assembly. It's really hard because some parts actually need to fit in this rubber bushings, and they're deformable. So the clearance is actually negative. So we propose this approach where we can just train everything in simulation on a single task, and then do the sim to real transfer onto a variety of difficult tasks in the real world. So we were actually really surprised by how well they worked. So this is how it worked. Let's see the approach. I think I'm clicking. No. The robots rebel. Can you restart? Always happens. AV problems are the hardest. 17? Just a guess. Almost. Okay, cool. So there's this, let me tell you, this notorious problem usually we encounter, which is called sim to real gap. Meaning, even with the same policy, you apply it in different environments. So you apply it to simulation versus in the real world. The resulting things can be very different. And so the difference, we call it gap, the sim to real gap. And here, for this kind of assembly task, we think the main difference between these environments is in the contact force resulted from the robot motion. So we tackled the contact force part. Cool. So our approach has two phases. One is offline phase, where we use an RL agent in simulation to generate data. No human demonstrations. We use the RL agent to generate data in simulation. and then uses the data set to train 2 neural networks. One we call it force planner, the other we call gain tuner. So the force planner plans not only the robot motion, but also the desired force when they're in contact. And the gain tuner adjusts the compliance gains. So in the online phase, in the real world, we have the force planner that takes in the actual trajectories from the robot and plans the next robot motion and the desired force. And then we have the gain tuner that according to the desired contact force, it plans the compliance gains for the robot. And this way, it modulates the contact force to the desired. Here shows you some examples of our tests. So these kind of insertion tasks, they're really tight. So the clearance is as small as 20 microns. And as a fun fact, you can see some of the pegs, they actually fall out of the gripper after insertion because it's so tight. And then we tested on what about different geometries, like electronic connectors, or the skateboard truck pieces we saw before, which has negative clearance. Then we also see failure case. One is, well, because the metal-to-metal contact can generate very large forces, it can trigger a protective stop on the robot. But the good thing is, if we just fine-tune the model with 10 trajectories in the real world, it works. Okay, the next one comes from, it's a collaboration with MIT. And this one looks at when we have assembly, well, so far we look at single step, but assemblies usually have multiple pieces. How do we decide on the sequencing of that? And it's called ASAP. So we automated the sequencing considering the physical feasibility of the, did it start? And so here is a very short video. It also has some captions, so you can read. But I'll just highlight certain things. It's not a trivial problem to figure out the sequence of an assembly, especially when we think about using a robot to learn to put the assembly together. It has to be stable. It has to be without collision. And so this work looked at what's the optimal way of figuring out the sequencing of assemblies. And not just one, but hundreds and thousands of them. So here we look at a large variety of assemblies, how they can be automatically sequenced together, considering the robot putting this together. So you need to think about the stability of the assembly during the process. Because in the real world, we have gravity. Cool. So in the end, you see in simulation, we have a robot arm to put the assemblies together, and then transfer that into the real world. In the middle is a rotary table that can change orientation. Here's to show in simulation versus the last frame, which is the real robot executing it. Cool. Since we're short on time, let's move to the last one. So this is a project we did with the whole team on autonomous assembly of this skateboard truck. We have a digital twin of the whole work cell, where there are 2 robot arms, and then the third one actually holding the camera. And once we verify the whole process in the digital twin, we can apply that in the real world. So everything is autonomous, but the sequencing currently for this one is manually defined. So the depth camera there estimates the pose of the parts. And there's a tool changing station on the side where we can change out different end effectors, different grippers. So even when the part is in hand of the robot, we need to do a pose estimation because there's always small errors. So there's force sensing on the robot, so it knows whether it's in contact, how much force it's sensing. We also designed some custom fingers for the gripper so that it can hold different parts. So this insertion is difficult because it's tight, but there's the learn policy. That's one of the rubber bushings I was talking about. And then there's a fastener tool that can fasten the fastener. Was that? Thank you.